Welcome to Yong Tuition. Happy New Year. Today we'll continue our discussing on Veritasium's big misconception about electricity. In particular, I'm going to discuss the origin of the mistake Professor Levwn had made on several occasions, namely how to apply Kirchhoffs' voltage law in the context or in the presence of the induced voltage. Let's go. I began with my talk with the report provided by Electro Boom. And this is the last part of this report, presumably prepared by instructor who is a colleague of Professor Levwn. But to my surprise, there are some apparent mistake exist in this report. Let's have a closer look. On textbooks that makes perfectly clear what is a voltage across an inductor is a textbook by Feynman. Richard Feynman again. I promise that this year I will talk about Richard Feynman again on big misconceptions in physics. But let's just return here. Obviously, this is part of the Feynman's lectures on physics, 1964 edition. In that textbook, the author stated explicitly that this integral through the inductor must be zero. Ooh, sounds familiar, isn't it? And they define the voltage difference across inductor, which is correctly identified as the electromotive force, which by Faraday's law, but this quantity, which has a unit of volt, has nothing to do with the integral through the inductor, which is zero, twice. Let's check, who said that? Who said that the voltage, the integral across the inductor is zero?
Action in the resistor. This side of the capacitor will become plus because of the current flow, and so
obviously it follows that the notation using the DC battery.
In the wire of the self-inductor?
So
what do I hear? What are you saying? It's zero, exactly because there is no resistance.
We're going to stop here. That's what he said, right? Let's just return to this report. That let's just jump to the final conclusion. In this sense, Kirchhoffs' voltage law holds, as argued by Modi, but one must always remember that the voltage difference across the inductor is defined in a very different way compared to the voltage difference across other three components. No. Electro Boom, you are played as a monkey. You have drawn a beautiful snake, but now you accept someone to put some eggs on your beautiful snake. Let's just have a look of what can be said on this claim. Here is a general description of RLC circuit in which that the inductors play a very important role. Now, in this second degree differential equation, you can see that we can treat the induced power and also applied power, externally applied power, explicitly. Okay, and actually, each term has a distinct meaning. The first term will be the voltage induced by self-induced by the inductor. And this second term would be a voltage drop according to Ohm's law. And third one would be voltage across a capacitor by definition. But care must be taken when you're dealing with this induced voltage. Here, the magnetic field flux is related to the current through the inductor. Okay, so this is so-called self-induction. Of course, to understand this RLC circuit, we can simplify this circuit into two distinct equivalent circuit. Namely, when the current is decreased in the circuit, we can replace the inductor by this battery. Notice, in this case, the positive, and please pay attention to the polarity of the battery. On the other hand, when the current is increased in the circuit, we are obliged to reverse the polarity of this equivalent battery. Okay. So that is why that is how the self-induction works in this circuit. Of course, we can discuss a special case when the external source was are replaced by the DC battery, as discussed by Lewin in his lecture. Now, in this case, we still can use the same idea to consider the two equivalent circuit, where when the current is decreasing, when the current is decreasing, when you switch off the circuit, and then you will see that the inductor acting as a battery, which actually help more current go through, because in this case, the current in the circuit is decreasing. On the other hand, when the current in the circuit is increasing, then the inductor acting as a battery, but in a different polarity, in order to resist the increase in current. These two phenomena can be well described by these two diagrams. So when the current is decreasing, as denoted by this diagram, the green colored curve represents a net current. So that is what we often calculated by solving that differential equation. We know that the current decay exponentially. But what we didn't say often is that the induced current in this case is in the same direction of the current provided by the battery. So this purple color curve will represent that induced current in this case. On the other hand, when you just switch the battery, the current will increase exponentially, as denoted by this green colored curve, that is a net current. However, in this case, we have to be careful that induced current due to self-induction is actually negative relative to the current provided by the battery, as denoted in this graph. Of course, this is just a sketch. Now, if you really want to go to quantitative, you will see that this non-linear, this is not non-stepwise increase in current is responsible, was caused by the induced current quantitatively. Okay, clear now? Now, let's apply the Kirchhoffs voltage law first. Actually, Kirchhoffs the voltage law is not the law, it's actually the rule followed by the Ohm's law. Okay. So, or by the definition of the electric field potential, because you cannot change the exponential at a particular point in the circuit just because you count the voltage from different direction. So basically what the Kirchhoffs voltage law say is that if just count the voltage drop or voltage increase across along the loop you choose arbitrarily, when you return to your starting point, you will see that the sum of these voltage drops will be always 0. Now, if we just apply the Kirchhoffs law here, we can see that this first term will be the battery, second term will be due to the resistor, third term will be capacitor, and last term will be due to the inductor. So if you just simply replace this induced voltage by definition, then you can got this equation straight away. Now the reason Professon Levwn insists that the sum is not equal to 0 because he didn't see something invisible. How can you see something invisible without imagination? That is problem. Now, what my point is here is that as many viewer have made the remark that Kirchhoffs law is perfect. You can apply Kirchhoffs voltage law in any loop you choose, whether it's a DC or AC. Okay. There's nothing wrong with Kirchhoffs voltage law. Okay. Something wrong is he didn't visualize the existed power supply in the presence of induction. Actually, if you don't mind, I can just alternatively call the Nernst law. We can use this equation to describe the Nernst law in order to understand the voltage induced by self-induction in this case. So you can consider the integral inside the inductor exactly. So this integral is exactly follows the curve. I will discuss this term here later. And secondly, the Maxwell-Faraday law is dealing with the abstract integral of any loop associated confined, given that the area or cross section defined by in this magnetic field flux. Okay, so this integral, in this integral, this E has nothing to do with the E Professon Levwn used in his lecture. The E he used is actually provided by the DC battery. Okay, so he seriously, the mistake is that he seriously believes that the, I call his criminal law, and he seriously believes that the voltage, the sum of voltage can be written as this, where is my, here. So this is the origin of his mistake. He just mixed up with the loop used in applying the Kirchhoffs voltage law and the loop defined in the Faraday induction law. So this E has quite different definition. So in the Faraday law, that this E is induced electric field. Okay, but in Kirchhoffs law, if you insist use the electric field, that electric field is actually provided by the source, the battery in his case. Okay. So that is why these, of course, if you didn't take into account of the self-induction, which act as a power supply, and of course, he cannot use the Kirchhoffs voltage law correctly. And here is what you can. So this I just repeat. If you want to use the Kirchhoffs voltage law, here is how to use it correctly. Okay. You can simply replace the voltage drop or by this simple formula. Okay. Now, this is my remark. It is wrong to subjectively make the sign of the induced voltage across the inductor as shown here. Oh, by the way, this equation eventually Levin used is wrong. He used a negative L di dt here because it's subjective. It is not follow the definition. Okay. Here probably you can read the reason I discovered here. How Levin made his mistake here. 1. Levin failed to treat the inductor as an effective battery in applying Kirchhoff's voltage law. 1. Second, in addition, Levin mistakenly wrote VL as positive L multiplied di dt while blaming other physics teachers as criminal. 2. Negative multiply negative being positive. So it would appear he's correct, but he made a mistake twice, unlike these poor physics teachers in his claim. Now, to illustrate these issues, probably we will just emphasize that what we are talking about. Okay. Originally, we are discussing the loop, and in which at the center there is a change magnetic field. So therefore, apparently, there is a current induced by according to Faraday's induction law, or should I say Henry Faraday's induction law. So this is not surprising. If you follow my previous video last year, then you can simply using Kirchhoff's voltage law to obtain that the total, the sum of the voltage will be 0. Okay, so that is a original issue when we discuss the debate between the electron boom and Professor Levwn. However, now in this case, if we just return to the general RLC circuit, then care must be taken. Okay, in this case, the E, I put the subscript here, I for induction. So E is induced, remember, by the changing of the current inside the loop. Okay. So you can consider there are certain amount of they are locally the magnetic field change inside or near the inductor. Okay. In this case, we cannot assume that the integral, no matter whether you use a positive or negative, as Richard Feynman used, you cannot equalize these two parts, namely the sum of voltage drop in the loop you choose and the linear integral, a closed loop integral of induced the field, electric field. You cannot do that. Okay. Do you still have trouble? Well, let's have a look at this diagram. Okay, I prefer to use a graphical method to explain some abstract principle in physics. Let's just use idea of equivalent. Let's use idea of equivalent circuit again. So these RCL circuit plus the DC battery can be replaced by this equivalent electrical circuit in which the self-induction is illustrated. Can you see that? I just replace this circle, which is perpendicular to the circle. Remember, this is a 3D diagram. We just replace this this symbol for the inductor by this loop perpendicular to the loop of this plane, original plane. From here, you can see that when the current increase, then the magnetic field across this generated by this current will increase. As a result, according to Lenz's law, some electron will refuse or will resist this change. It's just like Newton's first law of inertia. So therefore, the current I, so the subscript I here means the current induced by the change of the current provided by the battery. Okay, different current as I illustrate in that diagram. One is red, right? One is a green. So one is a green. When you switch on, one is green, that's the net current, and another is a purple. Okay, so this purple is what we call induced current. Okay, so when the current increase in the loop we discussed, and the current, the magnetic field will increase. Okay, as a result, some remaining or independent thinker electron will refuse the change. They will refuse the mandate, and so therefore they were just trying to move backward to resist this change, the external influence. So that is how the formation of this induced voltage appear. Okay. So by the way, if you do want to apply Faraday's law, you can follow this loop, okay, and by considering each part have acted by the induced electric field, you can still apply Faraday's law in this loop in order to work out that induced voltage. Unfortunately, all what we have discussed here is invisible. If you don't use this equivalent circuit, how can you see? Which is not true. Understand? Which is not true. So that is, I hope that explanation, the explanation I provided here will enable you to understand the origin of the mistake. Okay. This is just quite objective. Okay. If you want to know the how the inductor functions in the AC circuit, then you have to prepare to use both basic law correctly. Okay. If some teacher have trouble with using the basic law, that's their problem. Okay. So you cannot blame others because you make the mistake twice. Okay. As you can see that this video is kind of byproduct when I discuss our first video about the invisible battery. I promise you my next talk will be more interesting. I'm going to talk about the big issue, the big misconception about electricity originated from the Richard Feynman's hoax, namely quantum electrical dynamics. Okay, thank you for watching. Please don't forget to put a like, put some remarks, subscribe. Okay, thank you and goodbye.